On the last time, we talked about some various mathematical models. What we'll do today is apply some of those models to solve some very simple, straightforward differential equation problems. The first problem that we're given in differential equation to solve is called separation by variables. So you look at an equation to see if the variables are able to be separated. So we say that the variables are separable. If they're separable, then basically you can take a derivative and you can somewhat slice it up into differentials. So if it's dy over dx, I can multiply through by dx. So then I have a dy by itself and I have a dx by itself. If you have dy, then you want to associate with it the y terms. If you have dx, associate with it the x terms. And then thus integrate. You've separated the variables. You can integrate, solve for whatever variable that you're searching for. If it's y or if it's the velocity, or it doesn't matter. So that'll be the goal. It's kind of bright in here. That's better. This screen is weird. The screen has a way of kind of going down by itself. I don't know if you noticed that. Anyway, we talked about these before. The force that's behind an object that is falling, free fall, if you will, is said to be applicable to the law of motion. Here, that the force is the mass times acceleration, and that acceleration can be written as somewhat the derivative of the velocity. So we have the mass times dv over dt is here equal to the mass times the force due to gravity minus whatever type of resistance. And then secondly, we can apply the force to Hooke's law. And I'm going back over this because we'll look at a problem eventually, 2 or 3 problems, where they ask you to write a differential equation, either based on the falling body property, write a differential equation based on the equation of motion that is given to us by the vibration of a mass on a string. And then they have other questions. And most of the questions really come from this introduction. You can refer back to here to be able to build the differential equation. So this equation for the vibration of a mass on a string is equal to, is here, but let's go ahead and just pinpoint it, is this term here is equal to that. So the equation is m, the second derivative with respect to x, all over the time is equal to negative kx. So that may come up again. Dealing with circuits, very simple circuitry with resistance on it. The graph is down below. If we have something with the resistance and just an inductance, I'm going to try to build a differential equation based on here the resistance and the inductance. Here the inductance in terms of the differential equation is going to be here the resistance times the so-called current, and then the inductance is associated with the derivative of that current, di over dt. And according to Kirchhoff's law, that the impressed voltage that's dropped on a circuit is said to be the sum of the voltage drop on each individual component on the circuitry. So if you were going to build a differential equation, not based on the inductance here, this is the capacitance and the resistance, but it's a very simple one with resistance and the inductance is equal to this. So here we have here the inductance times di over dt plus r times I. I is a function of time. That's equal to the so-called voltage drop. And later on, we'll be able to actually solve that differential equation. But that's just the setup. It's a first-order linear differential equation. Here, simply based on resistance and also based on the inductance. So, next, we could talk about Newton's law of cooling. That first model up there. Secondly, talk about population growth or decay. Let's look at some problems making use of either population growth or decay, and then I think maybe one that deals with Newton's law of cooling. So the first one, sorry about that print so small. Here it says that suppose an experimental population of fruit flies increases according to the law of population growth. So they're giving us a hint in terms of what model we need to write first, or what equation that we need. So here it says that suppose that experimental population of fruit flies increases according to the law of the population growth. So it's some derivative. If we're talking about population, dp with respect to time, dt is equal to some constant times the population at present time. So p becomes a function of time. P is a function of time, and K is a constant. We call it the constant of proportionality. So it says that there are 100 flies after the second day of the experiment. So here, let T represent time. Looks like in days. So it gives us some initial conditions. It says that the population is equal to 100 when T is equal to 2. And then it says 300 flies, P is equal to 300 when time is equal to 4. Typically with these problems, they tend to try to give us what's happening initially, you know, when time is 0. Well, for this problem, they don't. There's a reason. They actually want you to solve for that. So it says approximately how many flies were in the original population. That is here. Solve for P when T is equal to 0. Now we're going to go back to the differential equation, which is here. I'm going to write it down here. This is dP over dt is equal to some constant times P. So we're going to separate the variables if you can. typically, very simple differential equations, you will be able to separate the variables. So here, separate the variables. So this is dp over dt. Multiply everything by dt. Divide everything by p. That'll get the dp and the p's together. And to get the dt separate from the p, because I want to separate the variables. Basically, you just get like terms together. So here, this implies that we have 1 over p times dp is equal to k times dt. You see what I did? Divided both sides by the p, multiply both sides by the dt, right? And I assume in this class I can do two things at once, right? You know, math 100, math 112. Oh, you skipped a step, you know. You did too many steps at once. So hopefully, you know, math 238, we can do a couple steps at one time. It'd be okay. So once we have the variables separated, then we're going to integrate with respect to each differential. Let me write those steps. Steps to solving differential equation by the method separation of variables. So one, we associate terms with their associated differential. That is, we get like terms together. What was that? Associate terms with their respective differentials. Let's say that is get like terms together. Secondly, once you've done that, you want to integrate with respect to the differential. So if it's dx, I'm going to integrate with respect to x. Right? So if it's dy, integrate with respect to y. So here, integrate with respect to the differential. So for this problem, what we have is the integral of 1 over p dp is equal to, k is a constant, so I can pull it out, times the integral of dt. So I integrate here, the first one with respect to the dp. That's just dp over p, so that's the natural log of p. Right? So here, it's the natural log, absolute value of p is equal to k times t, the integral of dt is just t, and then plus some constant. Let's call that c sub 1. Since we're solving ultimately for the population, we want to try to isolate p, get p by itself. What's the natural log? So the inverse of the natural log is the e base, so I can here, exponentiate both sides. So, exponentiating both sides yields for us e to the natural log of the absolute value of p is equal to e to the kt upstairs plus c sub 1. This is equal to, since e and the natural log are inverses, we just have here p, taking p to be positive, that is the population. Positive just makes sense anyway. This is equal to e to the kt, according to the property of exponents, that's times e to the c sub 1. So this is times e to the c sub 1. Here, let capital C equal to e to the c sub 1. Why? E is a base, it's a constant, 2.7, whatever, it's fixed. This c sub 1 is a constant. So a constant raised to a constant is also still a constant. See that? So here, the equation that we have is P is equal to C times E to the KT. Now in the algebra book, they just give that to the students. But in differential equations, we prove it. We determine where it actually comes from. So, you can say, since population is a function of time, it's the same thing as saying P of T is equal to C times E to the KT. Now we can finish the problem. We have the initial conditions. Let's go back up quickly. When P is 100, T is 2. When P is 300, T is 4. So we come back down here. It says that when P is 100, here T is equal to, was it 2? So this is raised to the 2 times K. So that's the first initial condition that we had. And then the second one was that when P was 300 flies, T is equal to 4. So this is equal to C times E to the 4K. Now, they want us to find the population when T is equal to 0. So that's the goal here. So notice from this first one, it doesn't matter which one you pick. So here from I, C is equal to, if I divide both sides by e to the 2k, C is equal to 100 times e to the negative 2k. I can't read that. Okay. So if that's the case, then what I'm going to do is take this C and substitute it over for that second equation, and let's see what we can do with that. So our goal is to eventually either solve for K or solve for C. So, and since 300 is equal to C times E to the 4K, let's take the C here. We say that this implies then that 300 is equal to C, but C is 100 times e to the negative 2K times here e to the 4K. And if I'm multiplying terms, if they have the same base, then I can just combine the exponents. So here, e is the same base as that e. So this implies then, divide both sides by 100, we get 3 is equal to e to the negative 2k plus 4k. It's just 2k. Well, we can solve for k. Take the natural log of both sides. So this is the natural log of 3 is equal to the natural log of e to the 2k So that's just 2k. Okay? Math funny, but anyway. So this implies what is k? K is equal to the natural log of 3 divided by 2. K is equal to the natural log of 3 all over 2. We always need the constant. So here we have P is equal to C times E to the KT. And I know that K is equal to this guy, right? And notice as I worked with that problem, I found C. C is equal to 100 times e to the negative 2k. I'm going to plug that in as well. So we say this implies that P is equal to C times e to the kt, but C is equal to 100 times e to the negative 2k, and then that's times the e to the kt. Now, it says find P when k is equal, well, find P when t is equal to 0. Go back up. Approximately how many flies were in the original population? That means that right at the initial, that's when t is equal to 0. What's capital P? What's the population? So find P when t is equal to 0. Well, let's see. Well, that becomes P is equal to 100 times e to the negative 2k, and this is e to the 0 because t is equal to 0. So here that implies that P is equal to 100 times e to the negative 2k, negative 2k. But I know what k is. K is an actual number, right? So here I have 100 times e to the negative 2 times k, which is the natural log of 3 all over 2. The 2's cancel out. I have 100 times e to the negative natural log of 3. So P is equal to 100 times e to the natural log of 3 to the negative first power, right? We can make that multiple as the exponent. And so e to the natural log, they cancel out. So this is 100 times 3 to the negative 1. That is just 100 all over 3. 33.3 dang on nasty flies. Right? So that's the number of flies that we have. And those son of a guns multiply very quickly. Here they go from 33, approximately about 33 flies in the beginning, and then in 2 days there's 100, then in 4 days there's 300. So you better get the raid out, or the black flag, whatever what they used to use back in the day, and spray those jokers and get rid of them. Yes, sir. This guy right here. Okay. It came from here, right? It came from the two substitutions of the initial conditions. 100 is equal to c times e to the 2k. 300 equal to c times e to the 4k. In the first one, solve for c. C is equal to 100 times e to the negative 2k, right? And then from there, if that be the case, then I'm going to take this value for c, plug it in right there. So I did that. So we said since 300 is equal to e to the c times e to the 4k, replace this c with 100 times e to the negative 2k. From there, just solve for k. Just divide both sides by 100. You can combine those exponents there. And then I think over here we just took the natural log of both sides. Yes, sir. Okay. All righty. Well, let's look at another one. Any other questions on that? Yes, sir. Either way, you'll get the same result. Yes, sir. Yep. It doesn't matter which initial condition you start with. Yes, sir. Yeah, it came from the property. Yes, sir. Yep. Now what I tend to do with my simplification is I try to do everything by hand. A lot of you all are sophisticated with these calculators. You can plug that thing in there up top, and you could plug it in. Let's see, where do we go? You can get that P. You could have plugged it in right here, 100 times e to the, right here, 100 times e to the negative natural log of 3. It would have given you 33.3, yeah, on your calculator, okay? Let's look at another one. This is the rate of decomposition of a substance. Here, that means that it's a negative, so instead of having the growth expanding, the growth is decreasing, diminishing. So the rate of decomposition of a substance is proportional to the amount y at time t. Put the differential equation there where k is some positive constant. Find k if y changes from 100 grams to 500 grams in half an hour. So let's see if we can look at the initial conditions. So the initial condition, it says find k if y changes. So here, when y is equal to 1,000 grams, comma, t is equal to 0. And then, when y is equal to 500 grams, here it says in a half an hour, so t is equal to, you could use 1/2, if you will. And so time is in terms of hours. So we have to solve this differential equation. We can solve by separation of the variables. Let's look at it. This is dy over dt is equal to negative ky. In other words, I can get the y associated with the dy. Then I can get the dt on the other side. So here, this implies then that if this is negative, I believe, negative, yep. If I divide both sides by y, we get 1 over y, multiply both sides by that dt, so this just leaves the dy is equal to negative k times dt. And then integrate. I can put the negative k in the front, since the negative k is just some number. Here times the dt, and integrate. So we get the natural log of the absolute value of y is equal to negative kt. And do like I did before, we'll say plus c sub 1. Exponentiate both sides. So this implies that y is equal to e to the negative kt, then up top still plus c sub 1. That implies that y is equal to, that's fine, e to the negative kt times e to the c sub 1. And so y is equal to some constant c times e to the negative kt here, where capital C is equal to e to the c sub 1. So this is the formula that we need. Y is equal to c times e to the negative kt. So with the initial conditions, that we go from 1,000 to 500 grams in a half an hour. So it's y is 1,000, t is equal to 0, and then when y is 500 grams, t is equal to a half an hour. Well, let's see. So here, what we're going to do is replace the y with the 1,000, and then also replace the t with 0. So this is c times e to the negative k times 0. Well, that implies directly that c is equal to 1,000, because e to the 0 is just 1. So here, c is equal to 1,000. So with c equaling 1,000, we have y is equal to 1,000 times e to the negative kt. So now we can find the constant k by using the second initial condition, that y is equal to 500 and t is equal to 1/2. So we say this implies that 500 is equal to the 1,000 times e to the negative k times 1/2. And so if we work with that, we get 500 divided by 1,000 is 1/2 is equal to e to the negative k over 2. Need to solve for k. So if we have an equation with some type of exponential, like this base e, we just take the natural log of both sides. So taking the natural log of both sides, this implies that the natural log of 1/2 is equal to the natural log of e to the negative k over 2. So we get the natural log of 1/2 is equal to negative k all over 2, because the natural log and the e base are inverses of each other. Right? So, what this came out to be actually is negative k over 2 times the natural log of e. The natural log of e is equal to 1. So solving for k, this is equal sign. Just multiply both sides by negative 2. So negative 2 times the natural log of 1/2 is equal to k. Let's see what the question there was, to solve for k. Is the natural log of 4 my answer? Is that the same as negative 2 times the natural log of 1/2? Is that the same thing? Kind of sound like the announcer with Batman and Robin back in the 60s, Will Batman and Robin make it from this gruesome chemical compound that the Joker has created? Join us next time. So is negative 2 times the natural log of 1/2, is that the same thing as natural log of 4? Just say yes so I can go to the next problem. But if you don't say it, yes, okay, we go to the next problem. Go ahead. I mean, do you see it though? You know, this 1/2 can be written as 2 to the negative 1, right? So if that's the case, this negative 2 in the front, which is the multiplier, becomes the power of the natural log, right? So you have the natural log of 2 to the negative 1 raised to the negative 2. You multiply those powers, you get negative 2 times negative 2, you get 4. Right? Yes, yes, sir. Yeah. So let's see. This is k is equal to, this is negative 2 times the natural log of 2 to the negative first power. This implies that k is equal to the natural log of 2 to the negative first power. The negative 2 becomes the power, so this is raised to the negative 2. So isn't this 2 raised to the second power? Well, natural log, excuse me. Natural log in front. So this is the natural log of the negative 1 raised to the negative 2 is just 2. So this is 2 to the second. So that's just the natural log of 4. Right? So same thing. Any questions there? Oh yeah, there's one, Newton's law of cooling. Newton's law of cooling. So since they tell us that we're using Newton's law of cooling, it says that the rate of change of the temperature with respect to time, so capital T is the temperature, is directly proportional, so that's some constant, directly proportional to the difference of the temperature on the object that you're considering minus the temperature of the outside, right? Whatever that surrounds it. If it's in the refrigerator, what's the temperature of the refrigerator? If you take this this specimen, you place it outside, what's the temperature outside? Place it in your room, what's the temperature in the room? So this becomes here T minus the temperature of the median. The median is the surrounding. Again, we can separate the variables here and solve that. The way I do it is I let T hat equal to T minus T sub m. And so, because this difference of T minus T sub m is a temperature. So it's still a temperature. So and T sub m is going to be a fixed term. Here it says in 1 hour when it was allowed to cool in air at temperature of 20 degrees. So T sub m is 20 degrees. That's going to be set there. So here I have dt hat, if you will, all over dt is equal to k times t hat. You separate the variables there, just like we did before. This becomes 1 over t hat times dt hat is equal to k times dt. We've had that form before. So this is integrating both sides. This is the natural log of the absolute value of t hat is equal to kt plus c sub 1. The same form from the previous two problems, right? So here we exponentiate both sides, and so I get e to the natural log of this t hat just becomes t hat, and that's equal to e to the kt plus c sub 1. And so this is t hat is equal to the constant times e to the kt, where c is equal to e to the C sub 1. But T hat is really T minus T sub m. Right? I made that claim. That's equal to C times E to the KT. That's the formula that we need. This is the formula for Newton's law of cooling. So now we can solve the problem. So it says the temperature of some kind of metal mold fell from 120 degrees to 70 degrees in 1 hour. So that means then that when the temperature was 120 degrees, the time was 0. And then in 1 hour, when T was equal to 70 degrees, the time is 1 for 1 hour. It was allowed to cool in air at a temperature. T sub m is 20 degrees. I think we have everything that we need to try to solve the problem. Let's see what it's asking for. How long will it take to cool to 40 degrees, and then you'll solve it for 30 degrees, and you'll solve it for 20 degrees, and then you'll see the pattern of what's going on. So here, they're not asking us to solve for the big term, like before, what's the population, and here, what's the temperature. They're giving you the temperature, and they want you to solve for little t, the time. Right? So here, given a temperature, we must find the time. Given temperature, find the time. So let's see. We have T minus 20 degrees. T sub m is fixed. 20 degrees is equal to C times E to the KT. They tell us that the temperature is 120 degrees when the time is initially. So when time is equal to 0. So I have 120 minus 20 is equal to C times E to the 0. Well, that gives me C is equal to 100. Are you with me? Okay. So then what I have is, yes, T minus 20 is equal to 100 times E to the KT. So it looks like we need to solve for K, for that constant up there, to be able to have the formula in terms of how it ought to look. So we can do that by the second initial condition. We have these two initial conditions here and there. So by that second one, when the temperature is 7 degrees, the time is equal to 1, we can solve for K. So here we have the 70 degrees minus 20 is equal to 100 times E to the K times 1, or just K. And so that gives us here 50 is equal to 100 times E to the K. So 1/2 is equal to E to the K. So take the natural log of 1/2. That's equal to the natural log of E to the K. That's a 2 there. And so this implies that K is equal to the natural log of 1/2. So here's the formula. T minus 20 is equal to C, we got that to be 100, times E to the K times T. So this is here, T times the natural log of 1/2. Now, isn't this the same thing? Let's see how you really appreciated arithmetic and algebra. Let's see how you really appreciated that. So this is, yes, t minus 20, yes, is equal to 100 times e to the, the natural log of 1/2. That's a dang on 1/2. Tell you, I really miss the old chalk days. And this is times t. Well, I hadn't done much, but let me see if I can do some magic, some abracadabra. We do a lot of that in math. We do a lot of abracadabraing. And have you noticed that in the past? Oh boy, it gets beautiful. So this is 100 times e to the natural log of 1/2. That's raised to t. Do you see that? Okay. You remember there was a law of exponent that said this. It said that if I had x raised to the nth power, and that's raised to the nth power, you can write that as what? X to the what? Huh? When you see a square. Yeah. N times m or m times n, right. Oh, okay. It still wouldn't be that. Oh. Yeah, it would be n squared. Yeah. No. Me too. Let's go over there. So, see, a lot of times, it's like this and you go there, but what if it's like that? You can always go back there, right? So if you have two powers multiplied, you can separate them and say this is a power and it's raised to a power. Now, the reason why I'm doing that is that, look, this is t times the natural log of 1/2. So this is a power of e, and this is also a power. That t is the power of e, right? The reason why I'm separating them is that there's a combination or relationship between the e and the natural log. They're inverses, right? So it'll cancel out. So it'll make the equation a little bit easier to digest. That's for me, because I come from the era where we couldn't use these calculators. So we have to try to simplify it as much as we can, and then once you get down, no, we didn't have anything like a graphing calculator. You better believe that. So let's see. So here, this is t minus 20 is equal to 100 times 1/2 to the t. If I have each of the natural log and each of the natural log, right? So that's no problem. So that cancels out. So I have left just that 1/2. And that's all of that is being raised to the tth power, right? I'm looking for t eventually. It says for the problem, what if the temperature is equal to 40 degrees? Can you find how long will it take? Can you find little t? So here, so now, so when t is equal to 40 degrees, what is t? So we have 40 minus 20 is equal to 100 times 1/2 raised to the, that's the t. So this is 20 over 100. So that's 1/5 is equal to 1/2 raised to the tth power. How do we solve for t? How do we get t by itself? Huh? Thank you, Michael. Yes, take the natural log of both sides. Because look, I'm trying to get t, but t is up in that exponent, right? So this is already in exponential form. If it's exponential form, take the natural log of both sides, right? If it's natural log, exponentiate both sides. You understand that, right? Principles apply to everything in life. Right? He's Christian, right? Christian, you're striking me with this hand right here. Just do it, right? I mean, come on, yeah. Just, well, you start here first. No, just go back, right? And you striking me, right? So I'm going to get him here. I'm going to try to dodge that, right? So look, if you think about it, look, this is what, his right hand, right? This is my left side, right? I'm getting him with the inverse. That's what that is. Right? You know what I'm saying? I'm going to try to get him too, right? Yeah. So we apply the mathematics to everything. So here, take the natural log of 1/5 is equal to the natural log of 1/2 to the t. I do that because I can bring that t down and write it as a multiplier, a factor, times that natural log in the front. So this is the natural log of 1/5 is equal to t times the natural log of 1/2. And so when the temperature is 40 degrees, t is equal to the natural log of 1/5 all over the natural log of 1/2. Now on your calculator, you can just compute that on just a regular calculator. Excuse me. And that gives us something around 2.32. And that time, I believe, was in hours. Yep, in hours. And so now for the next problem, I'll just set it up. Find t when the temperature is equal to 30 degrees. Right? So all you're doing there is just replacing here this 40 with 30. And so 30 minus 20 is equal to the 100 times the 1/2 to the t. And then you solve for t and just go through the same motion that we went there. Okay? Any questions? Now, I hope I can pick this up. What's the thing? Oh, there it is. Oh, no. Yeah, that's what I was about to do, yeah. Shouldn't have to go through all this, though, you know. Does anybody remember the Blues Brothers? That's a classic, right? Yes, you got to have everything that's needed, class, in order to go forward in this class. So
106 miles from Chicago. We got a full tank of gas, half a pack of cigarettes. It's dark, and we're wearing sunglasses. Hit it.
so you got to have everything you need, right? So by all means, I do not implore you to have cigarettes, but you got to have all the mathematical tools necessary, all of the arithmetic and the algebra and the trig, and just the basic calculus to be able to go forward here. And so once you have everything you need, bless you, somebody ought to say, hit it, right? So let's see. Number 15. A series circuit contains a resistor and an inductor, as shown in the figure there. Determine a differential equation for the current I of t if the resistance is R and the inductance is L and the impressed voltage is E. Do you know that differential equation? As a matter of fact, that's number 15, and then here number 16 deals with the falling bodies model, that F is equal to m times A. But here they say to write the acceleration in terms of the velocity. So here the acceleration in terms of the velocity would be dv over dt. Just the derivative, right, of the velocity would give you the acceleration. It says that here for high-speed motion through the air, such as the skydiver shown here in the illustration, falling below, the parachute is open, air resistance is closer to a power of the instantaneous velocity. So the resistance there that is repelling up against the MA, so it's MA minus some resistance, here is said to be directly proportional to the velocity squared. Can you determine the differential equation that illustrates that? So that's numbers 15, 17. There's one more, number 19. Here, based on Hooke's law for the motion of the vibration of a string, can you write the differential equation that exemplifies this? And I say, that's the question, determine the differential equation for this displacement of x of t. Those three problems you have seen already in our notes. So let me give you about 5 or 6 minutes to be able to write these three differential equations. And you can just look in the notes from what we just got through talking about in this section and find that information. So for this first one, did you see that this is L times di over dt plus Ri is equal to E? Did you get that one? Good. So you don't have to solve anything. We just want you to set up the differential equation. Later on, we'll work on solving those. We need some more techniques for that first one. Here, for this one, we know that we're using the force is equal to m times A, but they want you to use here to represent the acceleration, this derivative of the velocity. But then it says that it has resistance, right? So that's minus some constant. I mean, resistance is that k v squared. That's it. The next problem did you find this one here? This is still making use of Newton's second law of motion. here the acceleration is with respect to the second derivative of the displacement. So this is the second derivative of x with respect to time. Here, this is equal to negative kx. That was also in your notes as well. Right. The equation that we end up using for this is and we'll solve these problems when we get to that chapter. It's plus kx equal to 0, and then we divide through by the m, so we have this second derivative with respect to the time plus some k over the mass times x, that is. Is equal to 0. And then we let omega squared equal to k over m. And this implies that we have this second derivative plus omega squared times x is equal to 0. And this becomes the equation for harmonic motion. All right? Yes, sir. Right here. This is, look at this equation here. Do you understand this one? Just divide through by m. Even the 0 is divided by m, right? So, yes, sir. All right, by Newton's universal law of gravitation, the free fall acceleration A of a body, such as the satellite shown here in this figure, falling a great distance to the surface is not the constant g anymore. Rather, the acceleration A becomes inversely proportional to the square of the distance from the center of Earth. Here, that the acceleration is some constant divided by r squared, where k is the constant proportionality. Use the fact that at the surface of the Earth, here r is equal to capital R, just the radius from the center of the Earth to the satellite becomes proportional to the radius of the Earth, and that A becomes G to determine K. If the positive direction is upward, use Newton's second law and his universal law of gravitation to find a differential equation for the distance R. Sounds like a lot of stuff, right? Well, I think you go back up to the beginning and just try to walk your way through it, and it makes some sense. Well, first of all, what we're dealing with is that some force is said to equal to the mass times acceleration. So, so we know that. They tell us that here the acceleration is equal to k all over little r squared. And also use the fact that at the surface of the Earth, little r is equal to capital R, and that here A is equal to G. And from there, they want us to be able to write the differential equation. So here we have the mass times the so-called A. But A here is said to be this constant, and that's all over r squared, little r squared. But if this is the case, and if this is happening, then we have k is equal to a times r squared. And as you get further out, this k becomes the a, which becomes g, and then little r becomes capital R squared. And so here we have this force is equal to this mass times k, but k is said to be g times capital R squared all over here little r squared. And so that is that this mass, and since they're dealing with everything with respect to r, this becomes d squared r over dt squared is equal to, let's see here, if the positive direction is upward, that becomes negative, negative. This is negative mg r squared all over little r squared. And that gives us the second derivative with respect to r over dt squared plus, divide through by m, this is plus g r squared over little r squared. That's equal to 0. Well, we'll solve some of these guys later. Let me give you one last video, and I like this one right here. If you have trouble adding, this is good. We'll go home on this one. You may have trouble adding. If you do, you want to refer back to for a few dollars more.
Any trouble, boy? No, man. Thought I was having trouble with my adding. All right now.
Y'all have a good one.